students, in physics in the section heat. Now let us see another experiment. This is about the determination of specific latent heat of fusion of ice by the method of mixtures. First let us try to understand what is meant by the latent heat of fusion of ice. Look at this. Say 0 degree, 100 degree. Now what happens here? It's going to be ice. If it is below 0 degree, it's ice. Under normal atmospheric pressure, below 0 degree, it's ice. 0 to 100, it's water, the liquid state, solid state, liquid state. Above 100, it becomes steam. We all know that. So assume that you take an ice cube, which is at, let us say, minus 10 degree, and you heat it up. When you heat an ice cube which is at minus 10 degree, first thing, it will remain as solid itself, but its temperature will start going up. Minus 10 will become minus 9, minus 8, minus 7, likewise it will go up. But it will remain as ice itself. Ice cube remains ice cube. Solid states remain solid state. No change in that. Until when? Until it reaches 0 degree. At 0 degree also, it will be 0 degree ice. 0 degree ice. Continue heating it up. Give more and more heat to this. Now what will happen? It remains as ice for some time. It obtains all the heat that you give, and after some time it will change its state to liquid state. That is when the water will be produced. What will be the temperature of water initially? 0 degree. 0 degree water changes into 0 degree ice. 0 degree ice at 0 degree changes into water at 0 degree. Well, but that also requires heat. I gave heat, right? It was consuming heat not to increase the temperature, but just to change the state, So 0 degree water. To convert 0 degree ice to water, the heat required, 0 degree ice to become 0 degree water, the heat required is L. That is what we call latent heat. We mark it as LIW. That means ice to change into water, the latent heat required. Similarly, now it has become 0 degree water. Keep heating it up. When it comes to this point, it's going to be 100 degree water. 100 degree water. 100 degree water means it's water which is boiling. It has reached the boiling point. It's at 100 degree. It is not yet steam. Still water. It's in the liquid state. You give more heat. So 100 degree water at 100 degree absorbs more heat. Then what happens? It becomes steam. Initially it will be steam at 100 degree itself. Steam at 100 degree itself. Water at 100 degree becoming steam at 100 degree. For that, the latent heat required. 100 degree water becoming 100 degree steam. The heat required for that is what we call latent heat of vaporization of water. Vaporization of water. You can say Ws or SW, however. Right? After this point, it is again steam. Once it has come to 100 degree steam, then you heat it up, it becomes 110, 120, 130 degree steam. This is how the change takes place. Now what we are trying to find is this: 0 degree ice to change into 0 degree water, how much heat it requires. Clear? Right. So how are we going to do that? The concept: when small ice cubes are added, submerged and stirred within a calorimeter with water, the heat gained by the ice cubes to melt and obtain the equilibrium temperature will be equal to the heat lost by calorimeter, stirrer and water. See what we are going to do. We take a calorimeter, do proper lagging, that means insulate it, fill it with water, have a thermometer, have a stirrer, and you drop the ice cubes into this. Drop them in. So initially you measure the temperature, right? So you have calorimeter and stirrer. Let's say the mass is mc. Then you add some water. Let's say the mass is mw. cc cw. That's the specific heat capacity. Multiplied by, you know the initial temperature of this. You add some ice cubes. Then what happens? The temperature drops. Find the change in temperature, delta theta. Delta theta. This is what? Heat lost by calorimeter and water. Who is gaining this heat? We are dropping ice cubes in it, which was at 0 degree. First 0 degree ice cube changes into 0 degree water. For that it absorbs heat. After it becomes 0 degree water, again it has to come to an equilibrium with the water which is already there, because the water which is already there is going to be at a higher temperature. Why? Room temperature. So already the existing water is at room temperature. The newly created water, the water that has come from the melting of ice, is at 0 degree. Both of them have to come to an equilibrium. So 0 degree will increase. So let me say this way: m ice into L, that's the latent heat that ice requires to change the state from solid to liquid. After changing into liquid, still the mass is same. Mi is Mi. Still the mass is same, but now it is water. It is water into Cw into delta theta dash. Why delta theta dash? From 0 degree, it would have come to, so the delta theta here is different. For example, let's say initially it was 30 degree. Then let's say after adding ice cubes, it has come to 20 degree. Then delta theta is 10. Why? Water and calorimeter from 30 they have come down to 20. 10 degree is the change. Whereas delta theta dash means the water that came from ice cubes, that was at 0. 0 to 20 it has come up. So delta theta dash has to be 20. Careful. This is the heat gained by ice. So what happens if there is no heat transfer to and from the environment? Then you can assume these two are equal. Heat gained by one portion, heat lost by the other portion, both are equal. Simple. These two are equal. Clear? Right? So this is what we call the concept of this experiment is. So when we are doing this experiment, mass we can measure. We are going to use a 3-beam balance and find the mass. So all these mass we can find. Cc we usually take it as 400. That we can. Cw usually take it as 4200. Delta theta, since we know the temperatures, we know delta theta. So this thing entirely we know. Cw 4200, delta theta dash also we know. Only unknown quantity is going to be L. Right. So by equating these two, we know all other parameters other than L. Find L. That's what this experiment is all about. See how this changes theta 1 to theta 2. What is this? Calorimeter, stirrer, and the water which was already in. What is this part? What is this one? This is where ice changes into water. So it remains at 0 degree itself. 0 degree ice changes into 0 degree water. Then that newly added water, that means the water that has come from the fusion of ice, that's temperature increased from 0 to the new equilibrium temperature theta 2. So this is the newly added volumes temperature change. This is the already existing volumes temperature change. That was at theta 1, this is at 0. Both of them come to an equilibrium at theta 2. Clear? We will see how we are going to do the practical or experiment. Materials and apparatus, a calorimeter, a net stirrer. Net stirrer means, see, when you drop these ice cubes, you have to make sure they are fully submerged in the water. Why? If you just let the ice cubes be there, they will be floating. Floating means part of the ice cube is going to be exposed to the environment. So what? Then for the ice cube to get melted, for the fusion of ice, it will absorb heat from the environment also. Then I can't tell this story. What story? I can't say these two are equal. So we have to make sure ice cube doesn't get any heat from the environment. For that you have to ensure ice cube is full and fully 100%, it is submerged within the water. Clear? For that we need a stirrer which has a net-like arrangement in this part. So the moment you drop this ice cube, with this stirrer you can push it down. And you can keep it under and just stir it. Doesn't come to the top. It doesn't come to the surface of water. Right? That's what we call net stirrer. A thermometer, sufficient quantity of water. Sufficient quantity of water. See, if this is the calorimeter, we should not put too little amount of water. Why? Then when you put the ice cubes, you won't have sufficient water to submerge it. Right, problem number 1. Problem number 2, if there is too little water, once you drop the ice cube, the temperature will go down rapidly. It will go down significantly. Then what will happen? There will be mist forming around. That will have some additional complications. I will explain later after doing the experiment. When I do questions, I will show you when there is mist around, what additional complications it has. So to avoid all that, you need to have sufficient amount of water, but it doesn't mean full, because then you can't drop the ice cubes. That is also wrong. Keep it somewhere here. Usually we say 2/3 of the calorimeter's capacity. That's not a hard and fast rule, approximately, because it will have sufficient space for us to drop the ice cubes as well. This would be okay. So sufficient amount of water. Small ice cubes, not too big ice cubes, because you know how ice cubes gets formed. Let's say you take some water, maybe in a glass or something, and you keep it in the deep freezer. After an hour you go and check, part of that will be frozen. Another part. So if it is a big block of ice, the part which was frozen initially might go to minus degrees, minus temperature, when the outer surface is getting frozen. Because by the time outer surface is frozen, the inner one was frozen long time back, right? Few hours back. So it was already at 0, but it is still remaining in the fridge because the rest of it has to get frozen. Then what happens? Outer surface will be like, when you take it as ice cube, outer surface might be at 0 degree, but inner core of that ice cube may not be at 0 degree. It might be at minus 2, minus 3, minus 5 degrees, which will have error in our calculations. Why? We assume ice cube is at 0 degree. 0 degree ice cube immediately changes to 0 degree water. Then the water only temperature goes up. That's how we do the calculation, right? We don't assume ice cube coming at minus 2, from there it comes to 0, then changes to water. We don't do like that. Therefore, to ensure that ice cube is always at, like the whole ice cube has uniform temperature at 0 degree, better to have small ice cubes. Right. Second thing, big ice cubes take long time to melt. Then the interaction with the environment increases, there will be more heat gaining, heat loss and all that unwanted problems. Another problem, when you put a big ice cube into the water, let's say you want to stop the experiment at 25 degree, but since you have put a big ice cube, the end temperature might be even lower than that, resulting in dew and all that. So better have small ice cubes, Filter papers or blotting papers. Filter papers or blotting papers means like the tissue only, like the serviette tissue, but it's a thick one. It easily absorbs water. Why? When you drop these ice cubes into the water, you have to make sure there is no water on the surface of ice cube. Because we are carefully measuring the mass of ice cube, right? If you will add the ice cube with water around it, then the mass you measure is not only ice, it is with that water. Whereas you assume all the additional mass is ice, and all those additional mass take the latent heat to change the state. But if you are adding water which has already changed the state, don't you think it is an incorrect experiment? Don't you think it's an error in your experiment? So you have to make sure the ice cubes you add to the water are dry. There's no water on their surface. To ensure that, we use a paper to wipe it, which is what we call filtering paper. Filter paper or blotting paper. A 3-beam balance. It can be a 3-beam balance, 4-beam balance, an electronic balance, right? You can use any of these balances. If you just write balance in the exam, you might not get marks. You have to say particularly a 3-beam balance, 4-beam balance, or a electronic balance, chemical balance. Some special name has to be given for that. Right? These are the materials and apparatus. Look at the method. Measure the mass of the calorimeter with the stirrer initially. Fill about 2/3 of the calorimeter with water at room temperature and measure its mass, mc plus mw. Measure also this room temperature thing, I will explain when I do the experiment. We might not start at room temperature, we might start at a few degrees above the room temperature. I will explain when I am doing it. Measure also the temperature of the water. Θ1 is usually taken about 5 degrees above the room temperature. Why do we increase the temperature above 5 degree? Because if you start the room temperature itself, let's say you keep adding ice cube, let's say room temperature is 30, you keep adding ice cube. Let's say end temperature is 20. So 30 to 20 had been the range of your experiment temperature. Whereas when you were doing this, the environment was always at 30. So you were from 30 to 20 you were coming down. That means throughout your experiment, the temperature of this calorimeter and water was lower than the room temperature. Which means from the environment always there is a possibility of heat transferring in to the calorimeter and water, which we are going to change. When the room temperature is 30, you start at 35 and finish at 25. Now what happens from 35 to 30, when it reduces in that 5 degree range, the calorimeter and water has higher temperature than the environment. So, from the calorimeter and water to the environment, heat will be transferred. In the next half of the experiment, when the temperature is 30 to 25, calorimeter and water has lower temperature than the environment. Then it will gain temperature, gain heat from the environment. First half, you lose heat to the environment. Second half, you gain heat from the environment. We can assume the heat lost and the heat gained are equal. Approximately equal it will be. So that it compensates. Heat lost, heat gained, it compensates. Then we can ignore it in our calculations. Right, because of that we do this kind of an adjustment, a cooling adjustment. We started at 5 degrees above the room temperature and we will be finishing, we will ending the experiment 5 degrees below the room temperature. Wipe out water from small pieces of ice using filter paper and put those one by one into the water in the calorimeter while stirring, taking care to insert one piece after the previous one has dissolved. What is that? Drop one by one, don't drop all the ice cubes at once because then the temperature might go suddenly low. Add one by one, one ice cube, dissolve it, second one, dissolve it, third one, dissolve it, likewise step by step slowly you can go. Use a net stirrer to prevent the ice from floating in the water, that I already explained. When the temperature of the water has fallen sufficiently by about 10 degrees centigrade, stop adding ice, stir them. See, okay, let's say you started at 35, you are adding ice cubes, you have come to 25, stop adding ice cubes, still keep stirring it. Sometimes after that also, the temperature might go down. Why? Previously, temperature was not uniform. Near the tip of the thermometer, it might have been 25, but other places it might have been 24. So, when you keep mixing it, stirring it, it might come down to 25.5, 24.5. So, don't suddenly stop the experiment. Keep stirring it. Okay, you stopped adding ice cube, fine. Keep stirring it. You can see the temperature reduces. It comes to a point, remains there for some time, and again it will start increasing. Why it starts increasing? It's at 25, environment is at 30. You gain heat from the environment little by little. Then that lowest point of temperature is what we take as end temperature. Understand? That's what is mentioned here. Stop adding ice, stir the mixture well and record the lowest temperature of the mixture. Finally, measure the mass of the calorimeter with its contents again. With all the contents again, we will measure the mass. Right, with this mass, if we compare the previous mass, then we can find out how much of ice has been added. Clear? And we have to ensure one thing, the end temperature is not below the dew point. Suppose dew point is 26 degree, you do the experiment until 25 degree, then around the calorimeter you will get mist, which has more complications in it. When I do calculations, I will show you. Right. So, make sure, but if it's an air conditioned environment, then usually the dew will not happen. You won't have to worry about it, but under normal circumstances, non-air conditioned room, you will have to be concerned about the dew point as well. So, it's always advisable just to roughly check the dew point in advance and make sure you don't go below the dew point. This is what we are going to do. Let's see how we can do this experiment first. The material and apparatus required for this experiment are, we need water and a calorimeter with stirrer. We are using a special type of stirrer, you can see here, with a net kind of arrangement here, because when you drop the ice cubes within the water, usually they float. But in this experiment, you can't let the ice cubes float. Then the ice cube will absorb heat from the environment for it to melt. But as per this experiment, it has to absorb heat only from the water that is within this calorimeter. So, each ice cube we will have to submerge, we have to ensure it is fully covered within the water. For that, we will be using this stirrer. One by one, when we drop ice cubes, we have to submerge that within the water. Ice cubes. Ice cubes, when you use in this experiment, make sure you don't use big blocks of ice for two reasons. One, if the ice cube is too big, sometimes temperature within the ice cube may not be 0 degrees. One assumption we are taking here, the ice cubes are at 0 degree temperature. Imagine if ice cube is already at a lower temperature, let us say minus 5 degree, minus 10 degree, something like that. Then what will happen? As it is, that means when it is remaining in the solid state itself it will absorb heat to become to 0 degrees. But as per our calculations, we assume ice cube is going to be at 0 degrees. It absorbs heat only to change the state to liquid state. Therefore, you have to ensure the ice cubes are not too big, they are in a small size. Then we can assume the ice cube throughout its entire ice cube, it is at 0 degree itself. But because of that, don't use too small pieces of ice cube or small like dust like ice cube particles, because then that will be floating on the surface of water. It will be difficult for you to submerge them within the water. So, it has to be small, but not too small. That is what the ice cubes are. You need a thermometer to measure the temperature, and also we are using filter paper. Why do we need filter paper? When you drop the ice cubes into the water, you must make sure the ice cube is dry, meaning there should not be any mist or water on the ice cube, because we assume ice cube only is dropped within the water. It gains heat from the water, that will be the latent heat for it to change the state. 0 degree ice cube becomes 0 degree water, then 0 degree water comes to the equilibrium temperature. If you already drop the ice cube with water, that will be an error in the experiment. So, we use the filter papers to ensure ice cubes are dry. Then you need another calorimeter which is insulated. When we do the experiment, we have to ensure we don't allow the environmental heat to be absorbed by this calorimeter and water. Similarly, when the temperature of calorimeter and water is higher than the environmental temperature, it should not emit heat, it should not lose heat to the environment. The heat must be transferred from the water to the ice cube only. For that, we ensure, or the arrangement we have is an insulated calorimeter. Within this insulated calorimeter only, we are going to keep the calorimeter with water like this and do the experiment. There are three possible methods of heat transfer: conduction, convection and radiation. We are taking the measures to prevent heat loss to the environment in all these three methods. By covering this lid or covering this calorimeter with a lid, we ensure there is no convection happening. And having an insulation here, heat insulation here, we ensure there is no conduction happening. Even though there is no 100% prevention of conduction, to a certain extent we can reduce or we can minimize the conduction. Also, by keeping this calorimeter's outer surface bright or shiny, we can ensure that the radiation is also minimized. So, we take the measures to minimize the heat loss to the environment or obtaining heat from the environment. There are three possible ways: conduction, convection and radiation. We have taken measures to prevent all those three. And then we need a 3-beam scale. You can use a 3-beam scale, 4-beam scale or even an electronic scale, right, to get the measurements of weights. Right. First, now understand the steps. First, we will be measuring the calorimeter with a stirrer. Then we will fill this with water. Usually we fill up to 2/3 of this the capacity of this calorimeter, leaving space for us to drop ice cubes in it. Right. If you fill the water too much here, when you drop ice cubes in it, the space may not be enough, the volume may not be enough, and the water might spill out. That will result in error in your readings. If you take too less amount of water, problem number one, when you drop the ice cubes in that, the water may not be enough to cover the ice cube fully. Then the ice cubes will get heat from the environment. Second problem, the the change in temperature will be significant. Why? If the amount of water you have in the calorimeter is less. You understand now what we are going to do in this experiment? Usually we will measure the room temperature. We will start the experiment approximately 5 or 6 degrees above the room temperature, and we will end the experiment 5 or 6 degrees below the room temperature. So that even if we have taken all the measures, still if there is some heat absorption happening from the environment, when we start the experiment 5 degrees above the environment, it usually loses heat to the environment, and when it goes below the room temperature, it obtains or it gains heat from the environment. So it's a correction we are doing, starting 5 degrees above and and ending it 5 degrees below. We ensure, or we do a correction there, the heat gained from the environment and heat lost to the environment can be equal, so that we can ignore the fact that heat is being transferred from or to the environment. So imagine if room temperature is 30, we will be starting this experiment approximately at 35 degrees and we will be finishing at 25 degrees. If you take too little amount of water, when you drop the ice cubes, dramatically the temperature might go down. It might not stop at 25, it might go down even below 25. That can result in error obtaining or gaining more heat from the environment, right? So don't take too much of water, don't take too less amount of water. Usually 2/3 of the capacity of this calorimeter is the amount of water that we will be taking, right? So let's again go through the steps. We are going to measure these two, the calorimeter and the stirrer, fill with water to 2/3 of this and measure the weight, and make sure the temperature is approximately 5 degrees above the room temperature. One by one you drop the ice cubes, submerge them completely within the water, make sure they dissolve fully, check the temperature until it goes approximately 5 degrees below the room temperature. At that point we can stop the experiment, again get the weight of the calorimeter, stirrer plus water. Previous total weight and the weight now, the difference will give you how much of ice cubes we have added. Then what is going to be the calculation? Ice cube gains heat for two reasons. One, for the state change. From solid state it becomes to, or it changes to liquid state. 0 degree ice cube becomes 0 degree water. That is where it absorbs the latent heat. Then 0 degree water with the already existing water, already water is available within the calorimeter, which is at a different temperature. So those two will come to an equilibrium temperature. So 0 degree temperature, let's say equilibrium is at 25 degree, 0 degree water has to come to 25 degree, it again gains water, right? So that's the total, it again gain heat. So that's the total heat gained. And who is losing heat here? The calorimeter, stirrer and the already available water, they were at 5 degrees above the room temperature and they lose heat, and the equilibrium is arrived at approximately 5 degrees below the room temperature. The ice cube and the water from ice cube, the heat they gained should be equal to the heat lost by calorimeter, stirrer and the water. Equate those two and calculate the latent heat of ice. This is what we are going to do. So as the first step I explained, let's get the weight of calorimeter and the stirrer. Let's get the weight of empty calorimeter with the stirrer. It's below 100, above 30, but below 40. Can you see that? So it has to be above 30. Let's keep it at 30. Let's change one by one. 31, 32, 34, 35, 40. 35.5 gram is the measurement we are getting. 35.5 gram is the weight of empty calorimeter and the stirrer. Let us write down all these readings on a table, so that we can do the calculations at the end of the experiment. MC, the weight of calorimeter and the stirrer, is 35.5 grams. Let us write it here. What is the next step? We have to get the room temperature, and we have to get water approximately 5 or 6 degrees above the room temperature. Fill the calorimeter to approximately 2/3 of its capacity and get the weight of calorimeter, stirrer and the water. First, let us measure the room temperature. You can see here the room temperature is at 29 degrees. 29 degrees. Let us start the experiment approximately 5 degrees above that. Say, let us start at 34 degree and let us try to finish it at 5 degrees below that. That is around 24 degrees, right. So, let us get the water heated up to 34 or a little more than that. You can heat it up, let us say you can bring it at 35 or 36 degree and wait until it comes down to 34 degree. From 34 degree you start adding the ice cubes until it comes down to 24 degree equilibrium. I have the hot water here. Let us fill approximately to 2/3 of this calorimeter. The room temperature was 29 degrees. Let me check whether it is 34 or more than 34, because we wanted to have a gap of 5 degrees above the room temperature. Students, as you can see now, it is 37 degree. That is fine. We will get the weight of this. By the time we finish getting the weight, it will come down to 34 degree. Then we can start adding the ice cubes to it. Let us bring these to 0, make it 100, it is more than 100, less than 200. Let us increase 10 by 10, it is more than 110, but less than 120. So, it has to be in between 110 and 120. Let us increase 1 by 1. Now, it is at 0, the weight is 112.3 grams we are getting, 112.3 grams. This is what the weight of calorimeter, stirrer and the water within it. Let us write down that also in our table. So, the weight of calorimeter, stirrer and the water, the hot water within that is 112.3 grams. Let us write it here, MC plus MW. When you subtract these two, you can find how much of water we have added here. Now, what we are going to do? We are going to start the experiment at 34 degree. One by one, we are going to add the ice cubes. Make sure they are submerged completely within the water. And when they melt, check the temperature. Keep adding ice cubes one by one until it comes down to 5 degrees, approximately 5 degrees below the room temperature. So, we start at 34 and we will go until 24 degree and stop the experiment. So, theta 1 will be the starting temperature, theta 2 will be the end temperature. Then at the end we will measure the weight of the calorimeter and the water all together, that will be MT. Shall we start the experiment now? Now, let us keep this calorimeter with hot water within the insulated calorimeter. and let us measure the temperature. Students, now you can see the temperature is at 34 degree. Temperature is at 34 degree. Room temperature was 29, this is at 34. So, 5 degrees above the room temperature. Let us add the ice cubes one by one and mix it, stir it and see to what extent the temperature reduces. And you know, one by one we had to add the ice cube, make sure ice cube is dry, there is no water or mist on it, right. Dry ice cubes have to be added into that. Make sure the ice cubes you are adding are not too big, not too small, it must be in a small, but not too small. Let us add the ice cubes, we will take a small piece. Make sure the ice cube is fully submerged into the water. That is why we are using a stirrer with net kind of arrangement in it. You can see the temperature has reduced to 32 now, 32. Let us add another ice cube. Keep stirring it because the temperature will keep reducing. You need to find out the minimum temperature it reaches to. Now, it has gone down to 31 degrees, you can see that. Let us add another one. There should not be any water in the ice cube. Make sure the ice cube is completely submerged into the water. We need to continue this until we get 5 degrees below the room temperature. Room temperature was 29, so we have to stop this approximately at 24 because we started 5 degrees above the room temperature. Now, it has gone below 29, it is approximately 28. Let us add another ice cube. Use the stirrer to submerge it completely. It has gone down to approximately 26 degrees now. Let us add another one now, another ice cube. Add small pieces of ice cubes now because we are close to the end temperature. We want 24 degree. So, small ice cubes let us add now, because if we add a big one, sometimes it might go even below 24. Submerge the ice cube within the water. It is below 25. It has come close to 24 degrees now, you can see that. Don't stop stirring it, don't stop the experiment, because sometimes even below 24 it can go further. So, you have to keep stirring it and find the lowest temperature, the minimum temperature it arrives at. What will happen? It keep reducing. Once the equilibrium is achieved, it remains constant, the temperature remains constant for a while, and then after a while it will start picking up again, because from the environment there will be a little bit of heat transfer into the calorimeter. Even though we have done all sort of insulation, still there will be a small percentage of heat being transferred inside. So, we have to find out what is the lowest temperature. So, don't stop stirring it, or don't stop measuring the temperature once you get 24 degrees. Keep stirring it until you get a constant temperature for a while. Now, you can see it is at 24 degree, it does not change, it does not reduce further, it remains at 24 degree, then I can say the equilibrium is achieved. Equilibrium of what? The calorimeter, the stirrer and the water which was already in was giving the heat to the ice cubes. Ice cubes were obtaining that heat, there was a change in state, the solid state became liquid. Then the liquid also, it was at 0 degree water, that has to go up to 24 degree. Now, all the ice cubes we have put in and the water which was already in plus the calorimeter and stirrer have come to an equilibrium at 24 degrees. That is the end temperature that we wanted to measure, because we started at 34, 5 degrees above the room temperature, and we wanted to finish at 5 degrees below the room temperature. So, we started at 34 and we are able to finish it at 24 degrees. Let us write down all these readings on our table. Theta 1, the initial temperature of water and calorimeter was 34 degrees centigrades, 34, and we ended the experiment when it was 24 degree centigrade. So, theta 2 is 24 degrees. Now, we need to see the total weight of calorimeter and the water within that, so that we can find how much of ice cubes have been added to that. Let us see how much is M total now. Let us get the final weight of this calorimeter and water, but make sure there is no mist around this. On the surface of this calorimeter sometimes there might be mist, because now the temperature of this is below the room temperature, it is 5 degrees below the room temperature. There might be sometimes mist, so make sure you wipe it completely, there should not be any mist. Right. Now, let us get the weight of this. It is less than 120, so let us keep it at 110 again. Increase one by one. 115, no change. 117, no change, it's more than that. 119.9 gram is the weight we are getting, 119.9 gram. Final weight we have got 119.9 gram. So, you know, if you can get the difference between these two, that will give you the weight of ice cubes that have been added to this. 112.3, 119.9, that is 7.6 gram of ice cubes have been added to this, right. So, as I explained earlier, let us do the calculation and see how we can find the latent heat of fusion of ice now. You can see the readings we have got have been tabled here, MC plus MW. So, by getting the difference here, you can find MW. How much is that? Say if it is 36, you will have 76 here, 0.8 then. Check that, 1358, 1156, yeah, 1037. Theta 1, theta 2, Room temperature we don't need it anyway, but just to ensure we have taken 5 above, 5 below, we have recorded that. Total mass, from that if you can subtract this, you can find ice mass, which is 7.6 grams. 7.6 grams. Let's do the calculation now. What is the calculation? Heat gained by ice is equal to heat lost by calorimeter stirrer and water. Okay. Heat gained by ice, MIL, MICW theta 2 minus 0, calorimeter and stirrer theta 2 minus theta 1, no, theta 1 minus theta 2, right? Heat loss, MW, CW, MI 7.6 gram. See, all M's are going to be grams, so you don't have to divide by 1000. If you really want, we can divide it as well to convert to kilogram. L, MI again 7.6, CW usually we take it as 4200, theta 2 is 24 minus 0 will be 24 itself. MCCC, here we can take theta 1 minus theta 2 common, then shall I write this way? MC 35.5, CC 400, MW 76.8 by 1000. Into 4200. For both these, the temperature change is from theta 1 to theta 2, 34 to 24, 10 degrees into 10. Right? Carefully you have to solve this. Carefully you have to solve this. You multiply all this and then subtract this part, divide by 7.6. The answer for L you are getting, you have to solve it carefully. You multiply all these and then multiply this also and subtract it there. Finally divide by 7.6. You get, solve it carefully and see, you get 342,305 joule per kilogram. 3.42 into 10 to the power 5 joule per kilogram. Usually we study that as 3.3 into 10 to the power 5, but here we get 3.42. Experiments you don't get the exact theoretical answer because there will be small errors in the experiments anyway. So 3.42 is quite close. 3.3 and 3.42 is quite close. 3.42 into 10 to the power 5 joule per kilogram is the latent heat of fusion of ice we get. Clear? So you have gone through the experiment, you have seen how I did that. I have given you the explanation for each step twice before the experiment, while doing the experiment. Twice I gave you the experiments. Now let's take some past paper questions and see how to answer the questions on this experiment. Right, look at this question. This is an old one, A-level 1995. We'll see how it is. You are asked to determine the specific latent heat of fusion of ice using the method of mixtures, which is what we did. Yeah. Draw a labeled diagram to show the arrangement for the experiment that you would use. Very simple, very simple, very, very simple. Let's draw the calorimeter. With lagging. Then water. Then you keep a thermometer. Stirrer. Right. Let's name them. They said labeled diagram. Calorimeter, thermometer, net stirrer. That's all. We can't draw the 3-beam balance and show it here. You can't draw the ice cubes and show it. So this is the arrangement. Then you put the ice cube into that and mix it. Simple as that. If ice is available in the following 3 shapes, which shape do you think is best suited for this experiment? A large cubic shape, small cubes, or crushed ice. It has to be small cubes. We studied why small cubes. Small cubes, because if it is large cubic shape, the temperature may not be uniform within the ice cube. If it is crushed ice, a couple of problems. One, it will be mixed with water. You can't take the dry ice from that. Other thing, even if you drop it dry ice into the water, then submerging them within the water will be difficult, because that will penetrate through your net mesh or net stirrer. It will be difficult. So small cubes is ideal. State one reason each for removing the other shapes. Okay, we'll mention the reasons. Big cubes or large cubes, that's it. The temperature may not be uniform within the ice. There are other reasons as well. Other reason is like if it is large cube, when you put it in the water, you may not be able to submerge it fully. It will be exposed to the environment, resulting in obtaining heat from the environment. Another reason, once you put a big cube, the drop in temperature can be significant. It might go even below the dew point, resulting in further complications. And why did we avoid the dust or like crushed ice? Because difficult to separate from water. Difficult to separate from water. We have to put dry ice, not with water. So getting dry ice from crushed ice can be difficult. What are the 3 measurements that you have to take before adding ice cubes to the water? Before adding to the water, 3 measurements. 1, mass of calorimeter with stirrer. Mass of calorimeter with stirrer and water. Initial temperature of water. Initial temperature of water. Those are the 3 measurements we take before adding the ice cubes. Usually a measure is taken in this experiment in order to minimize the heat loss to the environment. What is this? Taking 5 degree above and 5 degree below. The initial temperature is taken about 5 degrees above the room temperature or environmental temperature, and ice cubes are added until it reaches 5 degrees below the room temperature, below the room temperature. Right? Next. What are the other two measurements that you will take after mixing ice cubes and water? After mixing ice cubes and water, what do we do? One is the lowest temperature of water. You know, after you stop adding ice, still you have to keep stirring it and monitor the temperature. The temperature might further go down. After a point, it will start picking up. So the lowest point is what you call the end temperature. That has to be taken. Unless you say lowest, you may not get marks. Unless you say lowest, you may not get marks. And the other one, mass of calorimeter, water and stirrer at the end. Those are the two measurements we take once the ice cubes are added and mixed well with the water. If the amount of water used in this experiment is small, such that it is just enough to dissolve the ice cubes, precise results cannot be obtained. Explain why. What is the problem of using little amount of water? I have already explained. One, you may not be able to submerge the ice cubes fully. One problem. Temperature drop might be significant, resulting in dew. Another problem. The ice cubes cannot be submerged fully into the water. The drop in temperature will be significant. Sometimes leading to dew. Right? Next. When calculating latent heat of fusion of ice using the data obtained in C and E, the temperature of ice cube is assumed to be 0 degrees centigrade. If the actual temperature of ice cube is minus 2 degrees, by what percentage would the calculated value of L differ from its actual value? This is something you have to think. Not from the usual steps and all. This is something that you have to think freshly and answer. Latent heat of fusion of ice is this. They have given that. Specific heat capacity of ice. Now look at this. Let's do a analysis and come back. Our usual working is this. We will say MIL plus mi cw theta. Theta is the end or theta 2, let's say. Theta 2. mccc mw cw theta 1 minus theta 2. If I take this as H1 and if I name this as H2, look at this. Our usual calculation would say MIL equals H1 minus H2. L is equal to H1 minus H2 over MI. This is what we usually do the calculation. H1 we will know all these parameters. We would have got the measurements, calculate, multiply, add, subtract, divide, do everything, get the answer. Now the problem is there is something missing. What is missing? The ice cube was not at 0 degree, it was at minus 2. So before it takes the latent heat, it would have taken heat to become 0 degree, because now it's at minus 2. Unless it's come to 0 degree, it is not going to melt. So the correct calculation would be, look at this, concentrate. Correct way of doing this will be MICI 0 minus minus 2. Straight away can I say 2 degrees? MICI 2 degrees minus 2, right? They said minus 2, yes. Plus MIL plus MI CW into theta 2 MCCC MW CW theta 2 minus theta 1. What is that? The heat lost by calorimeter, stirrer and water is the same. But that heat is used for 3 things now, not for 2 things. 1, to raise the temperature of ice from minus 2 to 0, which is this MICI. It's ice, it's not water. Ice from minus 2 to 0 it comes. Then it gets melted. Then the temperature of the melted ice cube, the water now, increases. So this is our H2, this is our H2, this is our H1. And this is the new thing, We'll just keep it as it is. You can say MIL, on the other side we have H2, H1, this also has to be subtracted, 2 MICI minus 2 MICI. So L will be, if you divide by MI, H2 minus H1 over MI minus 2 Ci. Now which one is correct? This calculation is the correct one. As per the information now, this is the correct one. This is the incorrect one. This is the incorrect one. Why? They missed this factor. This was missing there. This is the incorrect one. Compare the correct one and incorrect one. How much is the error? Compared to this here, 2 Ci is the error. Can you see? H1 minus H2. Oh, this is H1, yeah. This is H1, this is H2. Then it will be H1 minus H2. H1 minus H2, yeah. So that's the same. H1 minus H2 over Mi is same. H1 minus H2 over Mi is same. Additionally, minus 2 Ci is there. Earlier it was missing. So how much is the error? If you compare these two, you can find out the error is 2 Ci. Error is 2 Ci. Let me write that here. Error is going to be 2 Ci. 2.2 into 10 to the power 3. This is the error. What is the correct value of L? It's given. This is the correct value. If I do it properly, I should end up with that answer. But now I have an error of this much. So what's the error percentage? Error is this 4.4 into 10 to the power 3, whereas the correct answer is 3.3 into 10 to the power 5. To get the percentage, multiply by 100. They said error percentage. Yeah. By what percentage? By what percentage? So error divided by correct value into 100. That gives you 10 to the power 3, 100, 10 to the power 5. You can cancel these three. 4.4 over 3.3 means 4 by 3 percentage. Approximately 1.33 percentage. 1.33 percentage. So compared to the correct value, the answer is going to be 1.33 percentage erroneous. Right. I did a rough analysis here to find out how the error is building up. So I didn't put any like actual values, I just with the notations itself, and I found out an incorrect value, correct value, and find out, okay, the error is 2CI. Found the percentage of that. Clear? So answer would be 4 by 3. This part is something that you have to think before answering. It's not the usual type of question where they talk about the steps and the routine questions. No. The last part, G, is little tough. But my point for you, to get an A, suppose okay, you thought a lot and you still couldn't come up with an answer for this. You got this wrong, still you can get an A. Because this question had A, B, C, D, E, F, G. 7 parts. Only last part was difficult. You get all other 6 right. Because all other 6 were directly from what I have discussed in the class. Directly from what I have discussed in the practical. So get those 6 right. Still you can get A marks. So this is for like, okay, you are already an A. You are trying for a better rank. Coming into the merit list. Coming into the first 10 in the district. Coming in the first 10 in the island. So that is where like answering questions like this is going to score you. Right. Others, suppose if you get something like this in the exam and you don't know the answer, don't be panic. Right. Out of 100 marks, 25 marks you can still make mistake. 25%, 1/4 you can go wrong and still you can get an A. How wonderful that is. It's like if it is a 20-20 match, you don't have to hit a sixer for every ball, right? You can choose the balls, get sixers and good runs and win the match. So something like that only. You don't have to really get full marks for all the questions. Well, if you are going to be a ranker, yes, you have to. But getting a 3A, getting a good rank, still you can make a couple of mistakes and do all that. Why I am telling this is, don't get panic if you get questions like this in the exam. If it is difficult, think well. You will come up with some answer. Sometimes you might have done halfway through. They will give you half marks. End answer might be wrong. Still your steps were somewhat right. Half of the marks might be given. Right. So that is just 1 out of 7 questions we have done here. And this is also 1995 past paper. Remember, 1995 advanced level. We are going to see latest questions. What's the next one? 2005 paper. Note this, 2005. A student wants to determine the specific latent heat of fusion of ice using the method of mixtures in the school laboratory. A calorimeter containing water, ice and all other necessary items for the experiment have been provided. Should the initial temperature of water inside the calorimeter be below, above or at the room temperature? We take the initial temperature above the room temperature, right? 5 degrees above. Simple, don't talk too much. Simply say above. That's all they ask. Is it lower, higher or same? Higher. Done. Next. Give the reason for your answer in A above. You know the heat will be transferred out and transferred in and it will compensate. So we can say the heat transferred from the environment and the heat lost to the environment will compensate each other. Right. That's why we are doing this. Otherwise, what happens? You start at room temperature, you always keep going down, then always you gain the temperature, gain the heat from the environment. You are not losing anything to the environment. Right? So if you are always gaining the heat from the environment, it will have impact on you. It will be an error in your outcome. Whereas starting 35, coming to 30, in that 5 degrees you are losing heat to the environment. Then from 30 to 25 when you go down, you are gaining heat from the environment. It will nullify each other. Give 3 precautionary steps that the student should follow when ice is added into the calorimeter. What are the steps? What are the precautionary measures? One, make sure you add small ice cubes. Make sure ice cubes are small. Make sure ice cubes are dry. There shouldn't be any water on the surface of ice cube. Right? That will be an error. Make sure water doesn't drip when dropping ice cubes. Right? If there will be water dripping out, then that will have an error in your mass. What else can we say? Those are the 3 you can say. Maybe another one you can say. Make sure you melt it or you submerge it completely. Submerge. They asked for only 3. Fully in the water. Right? So you can write any 3 of that, you will get marks. Next, when stirring the ice and water mixture, ice pieces should not float on water. What is the reason for this? I explained this. Why shouldn't it float? Because if it floats, it will be exposed to the environment. It gains heat from the environment for melting. Then the calculation will not be right. Because we didn't consider any heat gain from the environment. We assumed the ice cube to melt, it gains heat only from water and the calorimeter, not from the environment. What is the reason for this? To avoid the ice cubes gaining or obtaining heat from the environment, for melting or for fusion. Right? It should not get heat from the environment. Next, what experimental procedure the student should follow when obtaining the final temperature? Again, I explained you have to wait. Even after you stop adding the ice cubes, keep stirring it. The temperature might further go down and it will start increasing again. The lowest temperature has to be taken. After stopping adding ice cubes, continue to stir and record the lowest temperature. Record the lowest temperature. Record the lowest temperature. Lowest. That point is important. Lowest temperature. Next. The student obtained the following data and information from this experiment. Heat capacity of calorimeter, not specific heat capacity. Heat capacity, that means this is MC. They have given MC itself, not C. Specific heat capacity is C, but they said heat capacity. And look at the units also. If it is specific heat capacity, joule per kilogram per Kelvin. But this is joule per Kelvin. Per kilogram is not there. Initial mass of water 100 grams. Initial temperature 35. Final temperature 25. Mass of ice melted is 11 grams. Calculate the specific latent heat of fusion of ice. So you can say heat gained by ice, heat lost by water, calorimeter, and stirrer. Ice cube 11 grams, convert to kilograms, L into MCW. CW they have given 4000. Theta from 0, ice cube at 0, when it melted water at 0 has gone up to 25 degrees. Then calorimeter MC itself is 40 and initial mass of water 100 grams, C 4000. These two have come down from 35 to 25, 10 degree. Careful, huh? This is MC itself, both multiplied together they have given. Let's try to solve this. This is, if I say 11L plus I multiply by 1000, then here you will have 100,000. 11 into 10 to the power 5 will be, this is 440. So 44 into 100. 10 is there. I took another 10 out, 100. The 1000 from here goes up. So 10 to the power 5. 11L will be 33 into 10 to the power 5. L will be 3 into 10 to the power 5 joule per kilogram. Joule per kilogram. That's the approximate figure. We usually take it as 3.3 into 10 to the power 5. Here we are getting 3 into 10 to the power 5. So when you get the answers, don't expect the answer to be exactly same as what we use in the theoretical answers, because they won't give numbers like that. Right. If it is close to the answer, fine. 3.3 is what we usually use. The answer we calculate and get is 3. Fine. That's good. Right, that's about this question. Next one. On another day, when the room temperature was the same, the student repeated the experiment with the same apparatus and with the same amount of water. Right, which means M did not change. MC and M water did not change. But he observed that dew was formed on the surface of the calorimeter when obtaining the final temperature 25 degree. So same 10 degree changes and all that they have done. But there was dew, probably that was a rainy day. The content, water content in the air would have been high, so the dew point was achieved quickly. The mass of the ice melted is 18 gram. See, the previous day experiment, it was 11 gram. Today it is 18 gram. 7 gram additional ice has been required. 18 gram. And the mass of the dew formed on the calorimeter is 0.86 gram. The mass formed is 0.86 gram. Assuming that dew point is 25 degrees centigrade and heat released by condensing water vapor is completely absorbed by the calorimeter, calculate the specific latent heat of vaporization of water at this temperature. I'll explain you. Listen. Listen. Now, compared to the previous experiment, here what's the other thing, additional thing happening? The water content, the steam in the air, right, steam in the air gets condensed into water. So when gas changes into liquid, it releases the latent heat. That 0.86 gram water, the dew, would have released the latent heat to become water. Who absorbed it? Who absorbed it? The calorimeter absorbed it. But still, calorimeter from 35 degree, it has come down to 25 degree. So what happened to that heat it absorbed? It has passed it on to the ice cubes. So final impact is on ice cube. Right. So the other day, listen, the 11 gram of ice cube, 11 gram of ice cube, it melted and it gained the temperature, it gained the heat uh, from where and where? Calorimeter, MC, that released heat. The water which was already there, that released heat by MC delta theta was 10 degree. Today it is 18 gram for the same calorimeter, same temperature change, same amount of water, same temperature change. But then why did we need 7 gram extra? The heat released by the dew, the steam when it condenses it becomes dew, that, let's say MSLS, this is additional today. That also has to be absorbed by the ice cubes. Even though initially it is absorbed by the calorimeter, it's finally passed on to the ice cubes. So that also has to be absorbed by the ice cubes. Which means this extra 7 gram of ice is purely because of this. Correct? Because this thing did not change. Right. So I can do this calculation. The extra 7 gram of ice, the latent heat for its melting, and after melting the temperature goes up to 25, that heat has to be given by this steam. When it condenses, it releases the latent heat. That should be matched. Understand? See how much of extra heat the ice has taken. And who released that? Not calorimeter, because same calorimeter, same temperature change. Not the water, because same water, same temperature change. So what is additional here? This one. So let's say, we'll write it this way. We'll say heat released by condensing water vapor is equal to heat gained by additional amount of ice. Heat gained by additional amount of ice. Heat released by water vapor will be 0.86 gram into LS. Heat gained by the additional amount of ice will be 18 gram, 11 gram, 7 gram into L. First of all, it has to melt. L just now we calculated, it was 3 into 10 to the power 5 plus that 7 gram has to increase its temperature. Now it has become water. After melting its water 4,000 is what they have given. Don't use the values you know. They have given 4,000 here. 4,000 into, from 0 it goes to 25. We need to solve this and get the answer. We'll see how to solve this. Let me clear this. All the thousands I can leave it. I'll multiply by 100 maybe, or by 10. 8.6 LS will be, here it is 21 into 10 to the power 5. I multiply by another 10, 10 to the power 6. This is 25 into 4,000 is 100,000. That is 10 to the power 5. I multiplied by another 10, so 10 to the power 6. LS 21,728 into 10 to the power 6 divided by 8.6. Shall we divide and see? 28, 8.6 means 14, 4.3. 140, 4.3, 43. 2, 86. 24, 240. 240 is approximately 6. More than 5. More than 5, it's close to 6. So I can say 3.26 into 10 to the power 6. 3.26 into 10 to the power 6 joule per kilogram. That is the L. Now, this is the complication. I told you we should let the dew form there. If dew is formed, this is the complication we are going to have. When the water vapor, it condenses into water, it releases heat, and that heat also comes into the calorimeter. That is going to consume additional ice cube. Did you see? 0.86 gram of dew has caused from 11 gram ice to 18 gram ice. 7 gram of additional ice has come there. This is the problem, which I did not explain much when I was doing the experiment because I didn't want to complicate at that point. Now I am telling you should not allow this. So before you do the experiment, better to find out what is the dew point and then do this experiment. Clear? Right. So that is a question which was from 2005 paper. 2005. Quite an easy one. Quite an easy one. Only the last part had a little bit extra work to do. Apart from that, it's easy. Now let's see another question. 2012 one. 2012. You are asked to perform an experiment to verify that the value of the specific latent heat of fusion of ice is 3.3 into 10 to the power 5 joule per kilogram using the method of mixtures. Some of the items given to you are listed below: a copper calorimeter, a beaker containing water heated to 45 degree, a block of ice. Prepare a list of other items needed to perform this experiment. What are the other items we need? We need a thermometer. We need a stirrer, ideally net stirrer, a mesh stirrer or net stirrer, however. What else do we need? Net stirrer. We need a weighing scale, yeah? Don't just say weighing scale, let's say 3-beam scale or 3-beam balance or 4-beam balance or electronic balance. What else do we need here? We need the filter papers to wipe the ice cubes. Filter papers. I think that's enough. That's all? Yes. Next. When performing this experiment, what steps would you take to minimize the heat absorbed from the surroundings? So what do? One thing, ensure the calorimeter is lagged properly. Second thing, start the experiment (5 degrees above the room temperature and end at 5 degrees below the room temperature. Actually, this question is to minimize the absorbed from surroundings. This second measure they have given in the answer, but understand that measure doesn't minimize the transfer. Maybe you can say the net transfer is minimized, okay, or else we can say it compensates the transfer. We lose some heat to the surrounding, we get some heat from the surrounding, it compensates each other. So ideally we should say the net transfer to the environment is minimized, right? Net transfer. If the room temperature is 30 and the dew point is 25, what values would you suggest for the initial temperature and the minimum temperature? See, you should not go below the dew point. We have seen in the previous question what happens when the dew point is crossed. There will be dew and all, right? So we have to make sure we finish the experiment above 25. right? Let's say you want room temperature is 30, right? You can't go to 25. Let's say I finish at 25, 25.5. So that means we have a gap of 4.5. The up 34.5. Or let's say I finish it at 26, then up it can be 34. The gap has to be same. Let's say I finish it at 25.8, so it's 4.2. Up also 34.2. Whatever the difference you have to the higher side must be the same in the lower side also. So let's give 34.5 and 25.5. Okay, give reasons. So there are two reasons that I explain. One, why I didn't go below 25, and the other, why am I taking up and down same amount, right? The two reasons, two things are to justify here. To avoid the formation of dew. That's why I didn't go near 25 degree. That's why I didn't go near 25. I didn't go below 25 degree. The other one, to balance the heat gained from surrounding and heat lost to the surroundings. Clear? Right. So this is why we take 4 degree above, 4 degree below. This is why we did not go below 25. Next. List the experimental measures that you would take before adding ice. Usual typical question, every paper they have asked this. Mass of calorimeter with stirrer. Mass of calorimeter, stirrer and water. What is the next one? Initial temperature. Initial temperature of water. Those are the initial measures. Before we add ice, the measurements that we have to take. What procedures would you follow when preparing ice, adding it and mixing it with water? When you are preparing, you have to make sure ice cubes are small. Make sure ice cubes are small. When you are adding, you have to say, make sure ice cubes are dry and water doesn't spill out. Oh, it doesn't drip out. Yes. Mixing it. When you are mixing it, you have to ensure ice cube is fully submerged into the water. Same question, same answer, same discussion every time. Make sure ice cubes are fully submerged in the water. Simple, very simple. Next. Write down the rest of the experimental measurements that you would take after adding ice. After adding ice, what and what do you take? The lowest temperature. Lowest temperature. Next one, after the lowest temperature, the next one, the mass of calorimeter, water and stirrer at the end. At the end. Okay. Usual stuff, there is nothing unusual. The last one. In this experiment, the measurements that are used to determine the mass of ice have to be taken more carefully and accurately. Explain why. Now, this is something you have to think. They are asking, why do we have to be extra careful when we are taking the measurements of mass? Mass of ice basically. See, if you look at the formula, MIL, MICW theta, MC CC theta 2 minus theta 1, or theta 2 minus theta 1 I can take common, MW CW theta 2 minus theta 1. When we did the experiment, you saw this was around 40 grams, this was 400, I am just putting some approximate values, this was around say 80, 100 grams, 4200 into 10. So, look at these values, this is 16, isn't it? 16, this is 5000, 420, so it's like 436 into 10, 4360 is what we are getting. And this is also a small figure, but L you remember 3.3 into 10 to the power 5 Mi. So, look at this, we are having few thousands, 4000 divided by 330,000. So, what will happen, since this is so high figure, Mi has to be a low figure. The value of Mi, value of ice will be very small value. When it is small value, the error will have a big impact. I will tell you an example. I am measuring the weight of a 50 kg cement bag. When I am measuring the weight of 50 kg cement bag, if I make a mistake of 1 gram, not a big deal. Out of 50 kilograms is 50,000 grams. Of 50,000 grams, I make a mistake of 1 gram, it's a very negligible, very small percentage error. I am measuring let's say 50 gram a tea powder, tea bag. Or think about the small tea bag that we use to make tea, like with the thread and all, it has like 2.5 grams of tea in it, right? In 2.5 grams of tea, I make a mistake of 1 gram. How big is that? It's almost half of it, right? 2.5 grams, 1 gram, close to half of it. So, when the measured quantity becomes smaller and smaller, the error percentage will be high. Therefore, you have to make sure you measure it carefully without making an error. So, when measuring 50 kg, making an error of 1 gram, don't care about it. When you are measuring 50 grams, 2 grams, 3 grams, then the error of 1 gram is significant. It can have significant impacts. So, you have to make sure you measure it carefully not to make errors. Same thing. So, let's say this is the explanation part. You don't write that for the exam. This is the answer. Since L is significantly high, the value of Mi, that is mass of ice, is too low. Too low. It's a very small value. Therefore, it has to be measured carefully to minimize the percentage error. It has to be measured carefully to minimize the percentage error. Understood? This is the reason why Mi has to, because when the values become smaller and smaller, the error percentage is going to be bigger. We should not allow that. We should make sure there is no error, measure it carefully. So every question, or most of these structured essay type questions, most of the parts are very straightforward, usual parts. Anybody who has done the experiment or anybody who has watched doing experiment can answer it. Usually, like last part, one part of that whole question, they keep a new thing that you have to think and freshly answer, which is also not so hard. If you think carefully, you can answer it. Clear? So that's all from that experiment where we found the latent heat of ice by method of mixtures. I have shown you past paper questions also. It's not so difficult. Practice all this. We will meet up with another experiment in heat.